Alright, so let's just pick up the last few little ideas here. If three vectors are, well, or any number of vectors, but we'll use the example that we just talked about. If three vectors are dependent, okay, so what we had was we had u, we don't want to use that one. We had u, I think we just said not to use that one. U equal to 1, 2, negative 3. V equals 3, 1, negative 2. And W equals 5, negative 5, 6. We found that they were dependent, and we had an expression for the solutions A, B, and C. Right there. Okay. Oh, we had the sign. I've got the signs changed. All right. So there's our expression for A, B, and C. There's the parametric equation for the solutions. All right. And we let t equal 1, and that led to this particular example. A equals 4, B equals negative 3, C equals 1, which is to say that 4u minus 3v plus 1w equals 0. Okay, so just as an example. So here's what we then did. We said, oh, well, then solving for w, we get w equals 3v minus 4u. Okay, we can build w using 3 v's and minus 4 u's. A better way of saying that, the official term that you want to use, the official language that we're going to be using is we say that we have written w as a linear combination of u and v. Okay, so you'll see problems that say determine if these vectors are independent or dependent. If they are dependent, like this case, then express w as a linear combination of u and v. And that's all we've done, right? There are actually many linear combinations that we could use. Like if we would have let t equal 2, right? Then a would have been 8, b would have been negative 6, and t would have been 2. And so then we could have used that through. Right? Look what happens. You have 8u minus 6v plus 2w equals 0. But if I solve for w, look what I get. I get w equals 3v minus 4u. Right? I get the same thing. So it doesn't matter what I let t equal. I can still express w as a linear combination of u and v. Okay, so that's what you're going to see in here. All right. So we talk about these, we've used the phrase vector spaces. Okay, a vector space is this group, this set of vectors. But there's a little bit more to it. We have to have these addition properties, and multiplication properties that we've went through. But more specifically, what we want to talk about is that in order to be a vector space, the space has to be what we say closed under addition and closed under multiplication. So what that means to be closed under addition, for instance, is if I take two vectors that are in the vector space and add them together, I get a third vector that's in the vector space. Okay, I get a third vector that's in the vector space. Okay, so that's what it means to be closed under addition. So let me give you an example. So show that V, which is the set of all points x, y, z, or vectors, such that x plus y plus z equals 0 is closed under addition. Okay, so this is This is what we call a subspace. Okay, so it's a subset of R3. R3 is just all of the points like that. And so we're just taking a subset of those points. And what does the subset look like? Well, x plus y plus z must be 0. So some examples that are in this subset. I could have the point 1, minus 1, 0. Right? Notice x plus y plus z equals 0. I could have 3, 0, minus 3. I could have 1, 2, minus 3. Right? Those are all points that satisfy this equation. Those are all points that are in this group V. Now, interestingly enough, this particular equation is a plane. So these are points on that plane. All right. So here's the question. We want to show that that this subspace or this subset is closed under addition. So that means if I take any 2 points, let's just use these 2 as examples. If I take those 2 points and add them together, 1, minus 1, 0, plus 1, 2, minus 3, I had better get a point that is still in V. And what does it mean to be in V? Oh, x plus y plus z has to equal 0. So let's add them together. If I add them together, look what I get. I get 2, 1, minus 3. Add those together, I get 0. So this is in V. That's an element of V. Like we said, this is an element of V. And look at that. That is an element of V. So now that's not the official way to show, but that's just a small kind of a practice example. Okay. So if I officially wanted to show this, I would have to say, okay, let's take 2 vectors. One of them we'll call A, B, C, and the other we'll call D, E, F, right? And I want to add those together. And remember, I want to show that U plus V is in this subset. Let's write this. U's got to be in V and V's got to be in V. Okay, capital V. All right, so if I add them together, I get this new vector, A plus D, comma, B plus E, comma, C plus F, right? That's my new vector if I just add U and V. Well, now here's the question. What does this component plus this component plus this component equal, right? The x component, the y component, and the z component of this new vector equal. So let's add them up. A plus D plus B plus E plus C plus F, right? I'm just adding them up. And I want to see if it equals 0, because that's what I need it to be. Because if it equals 0, then that means this is in capital V. So there they are added together. And just with a little regrouping, look what I can do. Right? I'm allowed to do this because of associativity. A plus B plus C plus D plus E plus F. Right? I just reorder these things because it's all addition. And hey, look at this. I know A plus B plus C equals 0. How do I know it? Because U, which is ABC, is in V. What does it mean to be in V? That your x coordinate plus your y coordinate plus your z coordinate, your x coordinate plus your y coordinate plus your z coordinate needs to be equal 0. And that's what I've got. Likewise, D or little v is in there, so that means the x coordinate plus the y coordinate plus the z coordinate has to equal 0. X plus y plus z. Oh, look at that. That also equals 0. So 0 plus 0 is 0. So look, the x coordinate plus the y coordinate plus the z coordinate. Oh, sorry. Yeah, that's what it is. The x coordinate plus the y coordinate plus the z coordinate equals 0. So U plus V is also in capital V, and V is closed under addition. Okay. So we've just shown that V is closed under addition. Now, in a similar way, we could show that it is closed under multiplication. All right. Now here's the deal. If you have a subset of a vector space, all right, we are dealing with the vector space R3, right? Because we're dealing with 3 dimensions right there. If you have a subset of a vector space that is closed under multiplication and closed under addition, then we call it a subspace. So you're going to see problems that say, hey, here's a set and it's defined by, some rule. Is it a subspace? What they're really asking you to do is to determine that it's closed under addition and closed under multiplication. All right. So those are the last little bits of this first section on vector spaces.